Good afternoon, everyone. I am K. Subramaniam. I'm currently a PhD student in the Department of Food Process Engineering, NIT Rourkela. I'm currently in my fourth year. So my research work is modification of biological macromolecules for food delivery system. So you know that today's topic is protein yield and protein purity, but it's very difficult to show in a 2 hour span to how to isolate or check the purity or what's the yield to calculate. So instead, what we thought. So that experiment is pretty simple. You can do it in your home institute also. What you need is NaOH and HCl. So instead, it's better to explain something which we can use to enhance the protein yield or protein purity. So something novel which you won't get in your home institute. So today I'm going to explain about the cold plasma and how we can use cold plasma to enhance the protein yield or protein purity. And I'll also throw some light on what is cold plasma. So first of all, may I know how many of you from undergrads or PhD or masters, so that I can know how detailed I should go. So how many of them from the undergrads? I mean, no, all of them are masters or PhD students, right? So have you ever heard of the cold plasma or plasma before? No. So this is the first time you guys are hearing. I think except her, she's here before, so she might have known. So I think you guys have seen cold plasma without realizing it. I think when you see in a rainy season, so you see that thunder, right? So there is a glow around that thunder world, like in a pink or purplish color. So that is actually a plasma. So actually, the process of generating plasma is very simple. So what you need is some energy in some form, enough to break it down into a molecule. I mean, ionize the gas. So here, what we have is a multi-pin cold plasma. So the energy source here we are using is electric energy. So this energy can be anything. So you can use a microwave also to use any form of energy that can break down gas. We can use. So what is cold plasma? Cold plasma is simply an ionized gas. And it's also known as the fourth state of matter. We know that usual three states of matter: solid, liquid, gas. So how we convert into one state to another? We give an energy in some form. Let's say ice. So we give energy in heat, so it turns into liquid. Then heat, then it turns into gas. So similarly, if you give energy to air in some form, so it will ionize. So that's called plasma. A plasma can be two types. One is the thermal plasma, and another is non-thermal plasma, is cold plasma. So thermal plasma's temperature is, more than 1,000 degrees. So which is of no use in food. So all we care about is the cold plasma or non-thermal plasma, which you can see here. The maximum temperature we can attain here is 60 degrees. So it's safe to use for the food. We can retain the nutrients and we can modify the protein. So why it's called cold plasma? It's not cold, right? What we call cold, if something below 0 degrees is called cold, but it's not cold, right? So it's actually a relative term. When compared to thermal plasma, the temperature is so less that scientists have given them a relative name like cold plasma. So you guys aware of the protein isolation principle, right? At least, do you guys have any idea? So how we isolate protein? Let's take a millet flour. So what do we do? First, we do defatting so that it won't interfere with the isolation. So sometimes we use chloroform and methanol to remove the carotenoids or something. So then we have a defatted flour with us. So what we do? Then we add some water, maybe 1:10 or 1:15, depends on the protein concentration in your sample. So then what we do? So we add NaOH. Actually, what we are doing is we are increasing the pH of the solution. So where protein unfolds and dissolves in water. So the rest of the biomolecules, let's say fiber or starch, they are not soluble at higher pH. So that means basic pH. So when you add and mix it, so whatever is soluble in the supernatant, it's protein, and what is settled down at the bottom, it may be fiber or all non-protein components. So what we do, just we centrifuge it and we take the supernatant. So what we have a protein solution, right? So then what we do, do you guys know the isoelectric point? So isoelectric point is a pH where the net charge of the protein is 0. So where it precipitates. So at higher pHs, actually proteins have a negative pH above the isoelectric point. So let's say if the proteins are having a same charge, negative charge. So obviously they repel each other, right? So they suspend in a solution instead of precipitation. Similarly with the lower pH, if it's let's assume the isoelectric point is 4.5. So any pH less than 4.5, so give a positive charge. So everything has a positive charge. They repel and they suspend in the solution, so they don't precipitate. So we carefully adjust to the isoelectric point, so where they precipitate. So whatever precipitates, we should not consider it as a pure protein, because no process is 100% efficient, right? So we call it as a protein isolate instead of protein, or a protein concentrate. So when we call protein isolate and when we call protein concentrate, so do you guys have any idea? So if the purity is more than 85% or 90%, we call it as a protein isolate. So if it is less pure, between 50 to 60%, so we call it a protein concentrate. So you have a concentrator isolate which have a 80% or 70%. We know that there are a lot of impurities. So we have to do something, right, to increase the purity. And same thing with the yield. So what is yield? So amount of protein we recover from the sample and to the total amount of protein actually present in the sample. So let's say we have 100 grams of flour which contains 50 grams of protein. So we isolated, but we only got 40 grams of isolate. So it may be having only 35 grams of protein. So that means we are not fully recovering the protein which is available, because there might be numerous reasons. Because for example, you have taken the flour, so all the proteins might not be exposed to the solute or solvent, so they are not getting soluble. So we have to do something to break the cell walls, so that we can extract maximum protein available. Okay, right. And there might be some impurities, or some allergens or some toxic compounds which we have to denature or inactivate, so that we can consume that to enhance the purity and safety of the protein. So there must be a way to do that, right? So a commonly used technique are the thermal techniques. We know that. But the thermal techniques are, we know that sometimes they denature the proteins, and it also reduces the nutritional profile. So we don't want that. So in search of that, we are exploring the alternative techniques, which are non-thermal. So like cold plasma. So cold plasma, as I said, so the maximum temperature can't be, it won't go above 60. So it can be a good alternative to the thermal techniques to enhance the protein purity or yield. So I will explain the parameters and protein chemistry first, so that you guys understand how it helps in protein isolation. So what happens? So here, let me explain the parts. So this is the voltage regulator. So here we can control the energy. So we have to give energy to that extent it can ionize or break down gas molecules. So that we can control from here. And there are two electrodes here. So the top one and the bottom one. So the bottom one is grounded. The top one is connected to the step-up transformer. So because the domestic electricity we get is not going to enough to produce a plasma, so we have connected it to the step-up transformer so that we can get enough voltage. So what we do, I'll show you how to keep the sample and later on. So so here there are different types of cold plasma systems. So you might have heard about, one is jet type, one is dielectric barrier. Here we are having multi-pin. Okay, so they have their specific applications. So the jet plasma widely used for the liquids. So it can't be used for liquids, but it can be used for solids, because you can see a wide plasma discharge area. So we can treat a larger surface areas. So so actually the important part is the reactive species we are getting. Actually they play a major role in the protein yield or the protein purity. So how we can control that? So actually the reactive species which we generated in the cold plasma completely depends on the feed gas. So here we are using atmospheric air as a feed gas. You know that atmospheric air is so complex. There are so many gases. So from the inert gases to oxygen, nitrogen. So the plasma chemistry is pretty complex. It takes years to, still people don't know how many species actually we are getting in the cold plasma. So actually it's very complex, but I'll try to explain in a simple terms. Maybe I'll just take one, two gases and explain. So actually the important gas which actually governs the protein characteristics is oxygen. We know that proteins are susceptible to oxidation. So I'll take oxygen because air has around 30, I mean more than 21%, around 21% oxygen and around 70% nitrogen. So let's take those two, and I'll just explain what happens. Then we can move for the demonstration. So what happens? So there is a gas here. So I mean air is there between the electrodes. So when I increase the voltage to certain level, so what happens? The electrons inside the gas molecules, they accelerate so fast when there is the, I mean, reach the threshold, some of the electrons can be knocked out because of the high energies we are supplying. So then we have a free ions, electrons maybe because they are charged, so we call it ions. So we have a free electrons. So since some of the electrons came out of the atoms, now they become ions. They have some charge, right? So we know that any ions, positive or negative, they are highly reactive. Number two, when you're giving energy, those electrons get excited and jump into higher energy states, right? So and they can't stay at high energy, so they don't want to get down to the lower energy. So they go to higher energy and come back to lower energy rapidly. So they make some highly unstable, and they want to react with some other compounds to become stable. So that is called excitation. The one is the ionization, I mean the electrons comes out, and third one is the dissociation. So let's say because of higher energies, let's say oxygen molecules can be split down into 2O. So now we have a two oxygen atoms. Those two atoms will be reacted to oxygen, form ozone, O3, and they can be reacted with nitrogen. Or N2 can be divided into 2N. So that N react with oxygen, nitric oxide. So there are N number of combinations which happen. So they are very highly reactive, and they are readily reactive, and they want to react and become stable. So what happens? So now we have a highly reactive plasma. So whenever, let's say you have a flour, let's say millet flour. So we want to isolate protein from that. So we assume there is a 20%, 20 grams of protein in that flour. So what happens? You clip cold plasma inside. So these bombardment of species and oxidation. So what happens? The cell wall get ruptured. I mean, so in the flour. So what happens when you go for the isolation? So it's very easy for the protein to get soluble into the solute. So that we can enhance the yield. And in the same way, cold plasma has been proven to inactivate the allergens. So you know that soy protein has allergens, so which is not safe to consume. So it inactivates allergens also, and it inactivates some toxins also. So we have treated our flour with the cold plasma. Now, if you use this flour and you compare with the untreated one, for sure you will get a significantly increased yield and a protein with a higher purity. So I'll show you how to use. You can't see plasma. Actually, you know that photoelectric effect, right? So when they excite and they come back to ground state, they release energy in some form, in the form of a light. So you get a. That's why you see color in the cold plasma. So actually, in the daytime you can see. Wait. So actually, this is the setup for ours. So during night time, if I run the cold plasma, you can see the plasma like this. So actually, since we are using the atmospheric air, the color would be this. But if you use inert gases like argon, so it will be kind of purplish. I'm not pinkish. So it depends on the gas we use. So and this is atmospheric pressure because and actually plasma can be generated in closed chambers also in under vacuum. Why they prefer that method is it's very easy to generate plasma at below atmospheric pressures in vacuum. So, but the disadvantage is you need vacuum pumps. They are very expensive, and you can't extend this to industries because it's not feasible in the industry. So this is the the next version of the cold plasma system. You can use atmospheric air, which is cheap. Obviously, there is no cost, and you can extend this area also, the electrode area, for the industry level also. If you want to see, you can see this is the picture taken from our equipment. Uh, so, so if you guys want to see, you can see that. First, we have to turn on the main switch. This is a little bit dangerous. Okay, come this side. So you have to be very careful because we are handling very high voltages, so it can be fatal. Okay. So the two parameters there are different parameters we can vary. So one is the voltage, obviously. So higher the voltage, more the breakdown of the gas molecules, higher the concentration of the species. So that's simple. And one more thing is the treatment time. So there is a, so you can set the time here. And there is one more. So for example, if you are keeping the flower, so mostly it's a surface treatment, but you want your species to go inside the flower. So there is a fan here, so which forces the species to enter into the flower or cover the other surface. So these are the three parameters you can control. So we have to increase the voltage slowly. Now you can hear the sound. You can't see, but you can hear. But you can't. I mean, there is a limitation to this equipment. You can't go to more than certain level. What happens? So it causes arcing. So it may cause fire also. So you have to choose the right voltage where you get plasma and you won't burn down your equipment. So you should be very careful. But it's very efficient and it's non-thermal. And this is a direct cold plasma system. Over there you can see another system, plasma water. So that's called plasma activated water. So it's called an indirect plasma system. So you can see here. So what we do, we directly discharge cold plasma into water. So the main idea is, I mean, when we discharge plasma into water, it forms those reactive species which are long-lived. Actually, the plasma species we generate here, as soon as you turn it off, they are gone. They're no longer active. There are few species, I mean, plasma species, they can stay maybe 20 minutes, 15 minutes, but since it's an open air system, so it will be scattered into the air, so you won't get the effect. But it's not the case with water. So that's why they developed this system. So you discharge first into water. So they can stay even for a week. So what you do, so you can take that water and you add it to into your proteins, flour or anything. So it even covers more surface area. Here it's just a surface treatment. So we don't know what's happening on the particles on the downside of the plate. So that's a more effective system. So you take water so that so it covers every particle and you can see more significant changes with the plasma water compared to the direct plasma. But this is effective for microbial inactivation. So because the concentration of the species is so high, so sometimes you get a 3-log reduction also. So if you guys want to look at this, so you can see. So actually, I mean, as I said, to produce any plasma, you need 2 electrodes and a voltage and power supply. So over here, the metal strip you're seeing, so they are the electrodes. So there is a pin inside this one, like a pin there. So there is a pump that continuously circulates water. So it comes here, the water goes again into the sump. So it repeats. Maybe you can vary the time depends on your requirement. So 30 minutes, 1 hour. So after that, you can take out that water. So you can use it for the protein modification. If you guys want to have a look, you can see.
So good afternoon, one and all present here. So this is a GAN course and this is the practical session for ultrasound assisted alkaline extraction of plant proteins. So what we do basically is that we have using this ultrasound for the treatment for extraction of plant protein for various plant protein extraction for various plant protein materials. So we know that alkaline conventionally cannot extract more amount of protein, but if we use non-thermal technologies, this is non-thermal technologies and we can use it for extraction of protein for better yield, extraction yield, purity and many more purpose, and it is also less time consuming. So why you are using this? Because it creates lots of small bubbles like after generating sound. What is the type of sound? So in class 12 we have heard that compression, rarefaction. So in the form of this create localized heat in the plant materials which disrupt the plant's cell wall structure and leach out the protein from the material. So what we are using in this system, so we are using this type of probe type sonicator. This is probe type sonicator and this is basically used to extract the plant proteins in an efficient way and less time consuming. If you use in less time, so it will extract better protein yield and better functionality. So why using this thing? from conventional to this ultrasound assisted extraction. Ultrasound gives more amount of protein, more amount of unfolding nature of the protein. So this is basically used for this purpose, that it will leach out the protein from the plant material which are in storage form. So basically storage form in that means that it is bound together with carbohydrate, fat, lipid, starch. So we'll give the pH of that pH which is highly soluble, that is alkaline in nature, and then we put the sample in the probe and dip the sample, and then we'll extract the protein through this ultrasound treatment assisted extraction. So basically this is the system which we'll use in this purpose. That is, we'll use the amplitude of higher amplitude, because if we give higher amplitude it will extract better protein, that is high intensity ultrasound assisted alkaline extraction. And if we give less time, and time will be variable. So first of all we have to fix the time. So first we have to check for 0 minute, 5 minute, 10 minutes, or many more. So, and also the pulse time on and off. So in this system we can set the pulse time, temperature, and also amplitude. By next we'll keep the protein solutions. This is the protein solution. So we'll put in this, we'll keep it as a cold bath. Let's check. Then we drag down the probe and keep it deep in between the beaker downward portion, and in between that should be in the middle of the beaker, so that it will give proper sound and proper compression and rarefaction, so that it will generate localized heat near the plant wall structure and destroy the cell wall of the plant material and extract the protein from that plant material. Then we'll keep this and we'll start the process for 15 minutes. Then it will go like this way. Then we have to check the temperature of the cold water bath. If it is high, then it won't work properly. If it is more less cold, it will work properly to leach out the protein from the complex material. So we'll see this after 15 minutes. So what will be the proper working is going on or not. So after that, after this treatment ultrasound, we'll take out the beaker and then we'll centrifuge. So we then compared with the conventional extraction, like after alkaline extraction, we directly centrifuge and then extract the protein, soluble protein, and then we adjust the pH to the isoelectric point. What is the isoelectric point? Their net charge is 0. They are same also, but we are giving the ultrasound for better extraction, for better purity and better yield. So that day Professor Mahesh Pujari sir told that if we do the genetic breeding, then purity will increase, yield will also increase. But in that case also, yield will also increase and also the purity will also increase. But it is also the best process from any other process, like enzyme extraction, like cold plasma treated, and many more thermal technology. But if we use this system, ultrasound assisted extraction, above amplitude 50 or 60, it should termed as not non-thermal, it should termed as thermal technology, because it is used high intensity ultrasound. But we are using at low amplitude, that is low intensity ultrasound assisted extraction. For better extraction we use low intensity. So that's why this method is efficient, green, and less time consuming.